Hi, am I audible?
Yes, sir. You're audible, sir.
Okay. Thanks, Adi. I'm sorry, everyone. I'm just trying to figure out how to get my video on so that we can get this started. Bye. Yeah, I assume I'm audible and visible.
Yes, sir. Both.
Yes, sir.
Yes, sir.
Okay. Hey, everyone. Just to confirm, I assume we are live, we're recording. Okay, fine. So I guess let me just introduce myself and we can get started today. Yeah, so I'm Bharat, and I'm a faculty in the aerospace department at IIT Madras. And I have not been able to join the last 2 weeks, but yeah, I'm here, so we can get this all started. And I would like to also just thank Adinarayan for sort of handling and being able to answer your questions, etc. He's one of our BTech. He's in our BTech program in aerospace engineering at IIT Madras, and yeah, he's doing really well there. So no surprises. But anyway, since I think this is the first time I'm at least virtually sort of meeting all of you, I just thought I'd take the opportunity to tell you why we do this and what is it that we're hoping you would take away from it. The program as such, the fundamentals of aerospace, the intention is to what is? Give me a minute. I'm still trying to put this in my phone. Yeah, so the whole point of the fundamentals of aerospace program is to just give you a flavor to aerospace engineering, and it in no way is exhaustive. It is in no way trying to encapsulate what actually happens, but it is an opportunity for you to just get a peek behind what are the possibilities, what do we sort of work on, and a chance for you to just ask questions and interact and just sort of have whatever queries or doubts you have clarified. That's really the whole point here. And in a broader philosophical sense, the idea is to just get you interested, not particularly in aerospace per se, but just engineering as a whole. Right. So we're just using aerospace as a vehicle to talk about it. But the idea is to just get you interested and to see for yourself whether you want to do it or you don't want to do it, right? Even if you don't want to do it and you're sure of it, that's actually a great outcome. You would rather not get into a program that you are unhappy with, and we don't want that also. So in some sense, if you find it to be extremely exciting, it's good. If you find it to be extremely boring and it's like, I do not want to touch this in a million years, we're happy to do that as well. The whole point and the way we've structured it is, yeah, we have these weekly lectures, which of course you're all privy to, and you sort of go through it and we talk to you about some concepts. But the whole point of this particular hour and a half is to just answer your questions, right? So you have some queries you want to ask. Ideally, we'd like you to keep it to what we discussed, but that's fine. Sometimes you may have a broader question. We have reserved the last week as such of this program to answer your next step questions. What can I do after this? I am interested in this. Where all can I apply? Blah, blah, blah. So the interest of this 1 hour is to mainly target whatever we saw in week 3, I guess, which was titled Air and Planes. And the whole point of that specific lecture was we started with big classification. Then we said, well, the air is sort of there around us, and all we really want to do is try and manipulate it in making it flow over certain objects. And we just want to see if we can fly. And turns out it's not all that trivial to do. And one of the key things we take away from, I think, week 2 is the idea of a shape that we call as an airfoil, which it'll help you move up so that you can lift whatever you want to lift. And the whole point of week 3 is to say, well, we have the same shape. Can we just slot it in different portions of an airplane and think about controlling the airplane, right? So that's the basic idea. We're sort of saying, let's say there is some fluid that's called an air. and we just want to study what happens when it flows over different shapes. And then we seem to have found a useful shape, and we call that shape an airfoil. And then we ask, can I replicate it? Can I keep reusing this idea? And that's really what we do as far as an airplane goes. And I think there's a picture in one of our, in one of, I think, just looking at, yeah, we have movable surfaces, we have flaps, rudders, elevators, ailerons, but at the end of it, they're all just airfoil ships. And we learn to do a little bit, we learn a little bit about the flow around an airfoil, and we sort of abuse it to its maximum to see how we can get an airplane to fly in a way we want it to. Right. So the most fundamental aspect of all of this would be fluid mechanics, where you're just interested in studying how fluids interact with its surrounding, which in itself is a fairly complex domain and so much to be uncovered. But you can also take it to an applied regime where we say, okay, you know what, I have some understanding. Can I use it for practical engineering problems, which in this case would be, an airplane. Anyway, the intention of me rambling on is only so much. What I would like to do is I would like to invite you to ask questions that you may have. And the way we'll do this is in a few different ways. Just raise your hand or type something in the chat box, which I find out how to do it here, but let's say it's possible. Um, and I am fairly certain we may not be able to answer all the questions that you have. So for that, I know you have access to a Google Sheet or something, or you have some avenue where you can ask your question formally. So what we do is we collect all the questions that we get, and then we write responses and we send it back. Sorry, Adi, you saying something? Sorry, you are muted. Okay, doesn't matter. Right. So with that, I'll just sort of stop here. And is there anyone who has any question you want to ask? Am I audible? Or have I just been speaking to myself for so long?
Yes, sir. You're audible. Yes.
I'm audible. Okay, so nobody has a question. That's amazing.
Uh, I think we can do it similar to last couple of weeks where we can just ask them to raise their hands and then we'll probably just start. But we
That's
can
fine.
do
Yeah, Baumik, I guess you have raised your hand. You can go ahead. Baumik Chaudhary, can you hear me? Yeah. No? Okay. Fine. Maybe there's some connection issues
Oh,
there.
sorry. Oh, yeah.
Hello? Okay. Someone else, maybe Vartika?
So am I audible?
Yes, you are.
Yeah. So my doubt was like we learned about three axes: pitch axis, roll axis, and yaw axis.
Yeah.
So pitch axis is for up and down, but
Okay.
roll and yaw, like what is the main difference? The main thing they do is help the plane to turn left or right. Then what is the difference?
Yeah, it's a good question. So I'm going to have start using props here. So let's see what prop I can use that's around me. Okay, let's say my wallet. Okay, let me flip it open. So I said it looks long. The pitch axis, if this is the front of the airplane, back of the airplane, this would be the pitch axis. So the airplane is perhaps, like you said, on the runway and it's taking off. You probably want to pitch up. If I turn it front towards you, this would be the roll axis where you effectively turn left or you turn right. The yaw is you just effectively rotate left or right. Right. So what effectively happens is when you think about an airplane that's sort of doing a turn, it is most likely just a roll component. There is no yaw component there. But let's say when you're on the taxiway and you're trying to turn the vehicle as you go from, let's say, the taxiway onto the main runway, that would be a pure yaw. So does that at least clarify the difference between the two axes in terms of, I'm just giving you some examples, but um, does that help at least initially? The way is, I mean, I'm perfectly fine if you say no. Actually, that's not helpful, and I'm intending for the session to be a conversation. So, uh,
Yes, sir.
could you maybe repeat your question again?
Yes, sir. My question, you've explained it. It was basically that what is the difference between your and role?
Correct. So, simply speaking, let's say we live in a three-dimensional world. So you can think of translations as being in three dimensions. I can move front or back, I can move up or down, or I can move left or right, right? So those are your three axes for translation. You can think of the same three axes for rotation. So you have axis one for rotation, you have axis two for rotation, and you have axis three for rotation. That's really it. So basically, we live in a 3D world. So we will need three independent axes for translation or rotation. So roll and yaw would happen to be two of those axes. That's it.
Okay, sir.
Okay. Um, who's next? Maybe Amanat?
Good evening, sir. Am I
Hey, good evening.
audible?
Yes, you are.
Sir, I had two doubts.
Yes, please.
One was you told us about flaps, like
Okay.
elevators and ailerons, they're all based on the principle of flaps. If flaps are not attached to the surface, how do we control, like, how do they go up and down?
Okay. That's question one. Fair enough. You had a second question?
That is uh, not related to this.
Okay.
That was related to that rocket building, wala. Was there a deadline for registering in that?
Deadline for registering for what?
There is a project now. We have to build a rocket. Rocket, nahi, sorry, robot.
Okay. Good.
Is there a deadline for that?
Your
Registering
robot
for
could
that?
be a rocket, your rocket could be a robot. No, I don't think there's a deadline, but it should be on the website.
It was not written, so I was just wanted to confirm
Why don't you
this.
just send an email? We are pretty
Okay,
prompt with responding to all of this.
ठीक है.
Our intentions are very clear. We want you to have fun. So
Okay,
we're not going to bump somebody off on. So just write an email. But let me come
okay.
back to the first question, right? So what is
Hmm.
a flap? How is it attached to the surface if it appears to be detached? Yeah. So again, I'm going back to my trusty wallet. Okay. So let's say this portion is the airfoil, and this could be the flap. Okay, it could be the flap, aileron, whatever you want. When we think about it in as an idealized scenario, we draw it as one airfoil and we draw a second airfoil with a gap in between, such that it appears it is not linked. But in reality, what happens if you look at the mechanical construction, there is actually, if this is the airfoil, there is a hydraulic section at the bottom which can extend or contract. When it contracts, it actually pulls down the back portion, and when it extends, it pushes the back portion. That's how we mechanically control the flap, aileron, or any other devices. So if you were to look at it, let's say from the top, this portion would be mostly empty, but you would see two hinges over it, pretty much to how you open a door. So even though you can open a door, there are two hinges where it is connected, but everywhere else there is a gap. That's exactly, or I wouldn't say exactly, that's a very good analogy for how a flap is connected to the main body. So you can think of the flap as the door and the main body as the wall or whatever it is. Does that help?
Okay, yes, thank you.
Okay, sure. Chandrasekhar?
Good evening, sir. I'm audible.
Yes, you are. Good evening.
Sir, I have a doubt that we have studied that flap, airlong, elevator, and rudder, sir.
Sorry, could you repeat that? Flap, elevator. My audio was a little off.
Flap, uh, flap, elevator, airlongs, and rudders. We have studied that, sir.
Yes.
In that, you have teached about the special case that delta wing.
Yes. Okay. Yeah.
Yeah, that I can't understand clearly, sir. How that all the function it does in one, sir.
Got it. That's an excellent question. There's some construction. Okay, so let's think about the fundamental. You're okay. Just to ask what your question is, you said there is a delta wing, and you didn't entirely understand what was the function of these objects.
Yes, sir.
Now, let's think about this in a sequence of steps. So first is you want an airplane to, let's say, pitch up, right? That's my intention. The only way we can do that is you want to create some sort of a moment, let's say about the center of the aircraft, such that it can rotate this way or rotate this way. An easiest example is think of a playground on a seesaw. You sit on one side of the seesaw and the seesaw will effectively rotate, right? You get off the seesaw or someone sits on the other side and they push harder. You, so you can rotate this object by applying a force on some end. That is the first principle to appreciate. That is, when you sit on the seesaw, you effectively impose or you exert a force on this system, and that system effectively rotates about its fulcrum, which is the center of the seesaw here. So that is step one. That is, you can apply a force at a distance away from where you want it to rotate, and you can get the system to rotate. We do the same thing on an airplane. You have a whole airplane. This wallet becomes everything. Okay, so you need to for once it's an airfoil, now it becomes an airplane. So let's say this is my airplane, and this is the center of the airplane. If I want to rotate something like this, one possibility is I could apply a force here. If I apply a force here, then I can make the airplane rotate this way. If I apply a force at the bottom, I can make it rotate this way. So if I have apply a force that is at some distance, you can rotate it. I can also apply a force closer to the axis and I will still get a rotation, but that moment is going to be smaller because this rotational force or moment, as we call it, or torque, is nothing but the how much force are you applying multiplied by the distance away from the force. So if it's a small force that's very, very far away, it would be just as effective as a really, really large force very, very close. But a small force that's very close is not going to do much for you. A large force very far away, yeah, it's going to create all sorts of moments for you. Okay. So now the question is, how do we get this to rotate? We said, let's create a force at the back and build. Now, how do we create this force? All we have are wings and airfoils, and that's it. Turns out, if you have a section of the airfoil that can rotate like a flap, right? Or some portion of the airfoil which can actually bend. Turns out the minute you change the shape, and that's really the critical point in all of this. What makes an airfoil special is only its shape, right? A circle, a square, a diamond, an airfoil. The only thing that's really different between all of them is its shape. So the challenge, one of the challenges in aerospace engineering is what is a good shape such that you can get it to do whatever function you want. We found out, I say we, but not me, but aerospace people over the last 150 years or so have found out that if you can bend the rear portion of an airfoil, like you can just cut it and bend it, turns out it will produce a lot of force in the opposite direction of the bend. Suppose this is the airfoil. If I tilt this down, I will create more force upwards. If I tilt the section up, it is going to create force downwards. It's a simple rule. You tilt the section down, you can create force up. Tilt the section up, you can create force down. So now what we do is we say, all right, very nice. We have the end. This is now my airplane again. We have the end portion here that we will tilt, let's say, down. If I tilt it down, it's going to create a force upwards, and that is going to effectively cause a moment. Think of it again like a seesaw, and you can cause the airplane to rotate. This is the fundamental idea behind what we call control surfaces. It's not as simple as a seesaw where someone sits. You have to change the shape and you hope the air flows the way you want it to flow. And then you get the force that you hope you think you're going to get. And then blah, blah, blah. Now, if you look at that, Adi, would you mind pulling up the picture from our previous lecture? I think slide 12, which shows the elevators, rudders, flaps, etc.
Just a minute.
Yeah. So I will just request everyone to just hold on for 30 seconds because it's much easier to show it with a picture than my wallet.
Yes, sir.
Yeah. No hurry, no hurry. Whenever you can. I'm still seeing the Zoom screen, but is that me or have you switched it to something else?
Are you able to view the screen, sir?
Okay. There we go. Yeah. Thank you so much. Okay. So now we have the same principle. Can you just mark the aircraft CG?
Sorry, sir.
Can you mark the aircraft CG? Just draw an X somewhere. And
Okay, fine.
there we go. Right. That's a CG. So now let's consider the elevators. Those are the orange bits. So if the orange bit moves down, if both the orange bits move down, then there is a force that's upward that is acting wherever the orange bit is. And then that's going, so now you have a force as he's drawn, which is acting a distance away from the center. And so you're going to be able to rotate the aircraft up and down. Same idea for ailerons, right? Which is on the wings, which is on the left wing and the right wing. Again, you can deflect it one way or the other. It will create a force and you can cause the airplane to rotate. Now, can you on top of this copy the picture of the Concorde, which was on slide, I do not remember. It was the last slide.
On top of this, sir?
Or next to it.
Okay.
Any,
Yeah, I think that's right.
okay.
No,
Can you mark the control surfaces in the back? So, outboard of the engines. Yeah, just the outboard ones. Let's not confuse with the ones. And you can maybe just highlight, draw a red.
Yeah, yes, sir.
Okay, draw the other ones in blue or some other color, no, because actually this helps.
Sure. Yes.
Thank you, and sorry I'm paining you on this.
No.
Yeah, this is fine. Okay, so now you have a red-blue pair on either side. Those are your control surfaces. Now there are a few things we can do here. Let's say if we tilt both of them down, right? If you tilt both of them down, then effectively you're going to create a force up. And again, it's the same idea as before, where you have a long distance to the aircraft center and the vehicle will effectively pitch down, right? So if you tilt both red blue pairs on the left and right down, then you can effectively make it pitch up. So this acts like an elevator. So if you move the control surfaces in the same direction, you can effectively get a pitch of the aircraft. So that is why we call it an elevator. But you can do something a little bit more fun. You can switch it. You can have one half moving up and you can have the other red blue pair moving down. Right. So it is possible that the left side of the airplane could be moving up and the right side of the ones on the right side of the airplane are moving down. So now you have an opposite deflection, which means you have forces acting in the opposite directions as he's shown over there, which means it will cause the airplane to roll. So the same control surfaces, if deflected together, will cause pitch. If deflected differentially, will cause a roll. So that's why we don't call it an elevator or an aileron. We smash the two words together and we call it an elevon. Okay, so that is a long answer, Chandrasekhar, to your question. I don't know if any of that made sense, so please let me know how that was.
Yes, sir. Understood, sir. Thank you, sir. Sir, and one more question, sir.
Please.
It's not questions. I request. Can I get that PPT, sir? The presentation which you are teaching.
Okay. Sorry, what is the question?
Possible? Is that possible, sir? Which you are teaching the PPT, the presentation, sir.
You want that to be shared?
Yes, sir.
I am not sure if that's possible, but since you have the video and it's all, you can pause it at any point. I think that should be fine. I don't think we can share the PPT. Sorry about that.
Okay, sir. No problem, sir.
Okay. Bhaumik, is your issue resolved now? Can you still have your hand raised? Do you have a question?
Hello, sir.
Yeah, hi.
Yes, sir. Sir, actually, last time I was unable to unmute myself.
Okay.
So my doubt was, why do Russian helicopters have double spinner wings on their top, while the rest of the helicopters have only one wing, the main wing?
Yeah. So, okay. So first, it's called a rotor. We don't use the word wing when it comes to a helicopter. So what you're referring to is one rotor above the other. That's called a coaxial rotor setup. And I believe that company you're referring to is the Kamov. Kamov is the only company, at least successful uh, commercial organization that makes these counter-rotating coaxial rotors. In most cases, you have what we call as a main rotor and another one in the back called the tail rotor. Coaxial rotors have some advantages, and one of the primary advantages why people stack one rotor on top of the other is to reduce the footprint. Because a conventional helicopter has one rotor on top and the second rotor, which is really far behind. So the length of the helicopter is quite large. Whereas when you stack one below another, you eliminate the need for the other tail rotor. So your helicopter can actually become quite compact. That's one of the big reasons why people use this coaxial configuration.
Okay, sir.
Sure.
Thank you, sir.
Hey, no worries. Nikhil, ready?
Am I audible, sir?
Yes, you are.
Sir, what is the use of spoilers on an aeroplane, sir?
What is the use of spoilers? What is the use of a brake in a car? The exact same thing, right? So it's you want to go. Okay, there are two answers to this. Okay, so what is the use for a brake in a car? You may say that it is to slow down, but someone else might look around and say brake is really what makes you go fast, right? So unless you can stop it, you're not going to go fast. So the brake has another effect of allowing you to go fast. Anyway, all that aside, when you land on the ground, let's say you are flying and you typically land at what is landing speed typically? It's around 200 to 250 kilometers per hour. Right, that's the typical landing speed of, and it's fairly constant. Even larger aircraft land at let's say 200 to 250 kilometers per hour. So you touch down at 250 kilometers per hour. How are you going to get yourself down to zero? That's the question. Typically, we have three options. One is to do what we do on a car is or a bicycle is to apply the brakes. But the problem with the brakes is typically the way these work are these are disc brakes. Right. So you have a spinning object, which is your wheel, and then you have a stationary object, which you just sort of smash into it, and you hopefully arrest that rate of rotation through pure friction. But the problem is when you have an object that's spinning that quickly and you try to arrest it with just friction, you're going to create a lot of heat. And the thermal stresses go up quite high, the temperatures are very, very high, and there's a very good chance you'll burn out your brakes. Then again, these airplane brakes are not made out of rubber, they're actually made out of titanium disc brakes. So it's okay, it can withstand that temperature. But however, that in itself might not be sufficient. So what we do sometimes is you have these surfaces on the wings. Coming back to my wallet again, if this is the wing, part of the wing will just open up, right? And it just acts like a huge barrier to the air. If you want to think about what this is, imagine next time you're going in a car or you're cycling and you stick your hand out, right? You stick your hand out into the wind. And if you rotate your hand slightly, you will feel an upward force, which is what we call lift. But what if you were to keep your hand perfectly perpendicular to the air? You will actually see a lot of force against it. That is technically what we would call the drag force, but for our practical purposes, it is a force acting in the opposite direction of motion. So that acts like a brake. So the whole idea behind the word spoilers is that it spoils the air and it increases the drag and helps you slow down. Right? That's really the work of the spoiler. The third option, I said there are three options. So there's a disc brake, there's a spoiler. The third one is that engines will have a small slot that opens out of it. So while an engine for during its normal operation is supposed to produce a force forward because that's the thrust component, there is a small portion of the engine which opens and it has the internal mechanisms which allows the thrust to be acting in the opposite direction. So while in normal operation, an engine is supposed to produce a force in the forward direction, you could do something to make it point to create a force in the backward direction, which would again act to slow down the vehicle. So brakes, spoilers, what we call cowl flaps on engines are all to slow down the vehicle. Does that help?
Yes, sir.
Okay,
Thanks, sir.
no problem. Hetty? Hetty, are you there or? Maybe an audio issue. We'll figure it out. Gia, do you have a question?
Am I audible, sir?
Yes, you are. Please go ahead.
I had a doubt about regarding ailerons. Are they similar to the function of flaps or not?
Oh, or not. Okay. Fine. Um, Functionally, they are different, right? Ailerons, flaps, rudders, elevators, they're all the same idea of having an airfoil with the bottom or the trailing part movable, right? In that sense, they're all the same. What really separates them is where you place it on an aircraft and how you use it. Flaps are typically deployed together and they are towards the inner sections of the wing, and their primary role is to generate more lift so that you can fly the aircraft at a slower speed, right? So we briefly looked at this. So you have an airplane. If you want it to be, the airplane weighs something, right? Let's say 100 kilograms. I mean, it's a really light airplane, doesn't matter. It weighs 100 kilograms. And let's say you're traveling at some 20 meter per second, and you have built your vehicle such that at 20 meter per second, if you fly, the wing is going to generate 100 kilograms of force so that the airplane is going to be balanced. But what if I want to fly slower? Let's say I don't want to fly at 20, I want to fly at 10. If I were to fly at 10, then the wing is not going to be able to produce as much lift, and therefore you're going to start to sink. That's not ideal. You don't want to do that. So we want to find a way to, we want to ask the question, well, can I fly slower but still generate the same amount of lift? Turns out you can if you do the same trick we've been talking about today, wherein you deflect the rear portion or the trailing portion of your airfoil. Those are exactly what flaps do. Flaps are deployed so that you can create the same amount of lift at a slower speed, which is why you see flaps being deployed when you land, because ideally you would like to land as slow as a speed as possible. You don't want to come in really, really quickly because both safety wise and runway length wise, that's not very good. So flaps are typically deployed during landing. Um, the aileron is a function wherein you want to cause the aircraft to roll. It's the same idea of tilting the trailing portion of the airfoil, but now you keep this airfoil section at the ends of your wings and you differentially deflect it, right? You, if one moves up, the other one moves down, and vice versa. That allows the vehicle to effectively roll, right? So in short, they're all the same device placed at different portions that makes it functionally different. Does that help?
Yes, sir. Thank you.
Okay, sure. Jia, do you have a question?
Hi, sir. Good evening.
Hey, good evening.
Sir, this is a little out of the syllabus, rather.
Okay. Very
But
well.
so basically, the whole idea we discussed was that to gain a higher lift and lower drag, we try to make the aircraft streamlined and airfoil shape. And we try to reduce the weight or streamline the fuselage even more to prevent drag. But like we have heard of UFO encounters and seen images where their aircraft shapes are very against what we do. Like there will be like disc shaped, or there have been tic tac UFOs also, which have the fuselage very big and bulky. So,
Yeah,
can these somehow be explained using what we know as of now of aerodynamics?
that's a great question. That's actually a great question because you went all the way from UFOs to bringing it back to aerodynamics. Yeah, so UFOs are, I don't know, unidentified flying objects, or if I'm cooking something, identified fried objects. But either ways, we don't know the exact what they are, which is why the U stands there. Now, your question is fair, though. I mean, I can't comment on what exactly they are because we don't really know it. But it's a nice question in that, are these shapes that we see, can they be aerodynamic, right? And I think that's a good question because we typically think of moving in space based on something has to be aerodynamic and it should cut through the air quite clean. But you can also find instances of uh, objects that are just bulky and appear non-flyable that can actually fly. So let's take a satellite, for example, right? If you've seen a picture of a satellite, it doesn't look aerodynamic. It in fact looks like a big box with a large solar panel attached to it. It's not exactly something that can, what we would conceive to fly. But you can still control it, because what happens on a satellite is you have small rockets that you place all over that can fire in small bursts that can effectively create a force, and it'll let you do the same three things. You can translate in three axes, you can rotate along the three axes, and therefore you can fly. Argument to that is, yeah, we're in outer space, there's no real air here, so how does it really matter? You can think of the same idea and you can bring it back to Earth. And there's an aircraft called the F-35, right? F-35 Lightning. It's, why, I don't know, 5-10 years old, which is still latest generation. One of the things it can do is something called vector thrust. It's an airplane wherein the engines can point down and you can push upwards. So this is an airplane whose maybe conceivable idea for us is it should move quickly in this direction, but it can actually move vertical. It's not at all streamlined in that direction. You just have obnoxiously powered engines pointing down, which can push you up. So the idea is, yes, you could come up with ideas which will create sufficient forces in different directions. Perhaps what we did not very clearly talk about when we're thinking about airfoils and streamline this, we want to achieve that in the most efficient way possible. I want to try to do this with the least amount of energy. Right. So even a clunky shape like an airplane to move up and down can be done with very overpowered engines, which is what the F-35 Lightning does. It also has a slight fan in the middle, but it doesn't matter. A classic example of vector thrust would be the Sea Harrier, which is a plane that was designed a couple of decades ago. Now, coming back to your question on UFOs, right? There are a lot of technologies that we are researching. We're thinking, again, we being the aerospace community as a whole, there are a lot of really nice ideas with electromagnetism, plasma injections, boundary layer control. All of these appear futuristic, but you're able to create, at least on a lab scale or a numerical scale, you're able to show that you can get some of these out of the world or out of the way ideas to generate forces in different directions. So it whether we are there as humans to be able to do it, perhaps not. It's a little far away, but it is conceivable that there are these technologies may mature into what we are unable to understand right now. A word of caution on UFOs also, we only see photographs and we see small snippets of videos. There's a world of difference between something flying level for a long time and something flying in a ballistic trajectory. Right, I can take a big boulder and throw it, and I could take a snapshot of it a few seconds, and it looked like you have a stone that's flying through the air, right? But that's a very small snippet of, perhaps if you had the full context, you'd be like, yeah, that's really not flying. That's just a rock being hurled into space, right? So unless we can get proper evidence of these things, verifiable evidence, right? Not someone said it, someone posted it, something that you can actually verify for yourself. It's hard to comment on what exactly these UFOs are. I don't know what I did to answer your question. Hopefully, it was not.
No, sir, that was really helpful.
It
Thank
was
you.
a fun question. Yeah. So thank you so much for asking.
Thank you, sir.
Yeah. Let's see who I'm going in sequence of hands I saw raised. So I think uh, sorry, who is this? I'm sorry, I can't see. Okay, doesn't matter. Can Abhishek, do you have a question?
Yeah, hello, sir. Good
Hey,
evening.
good evening.
So my doubt is that usually for like if we take an example of an airplane, it generates thrust using an engine, right? That depends on the air density for combustion and propulsion, right? So
You
then,
write
so
the
then,
question. Okay, go on.
y- yeah. So then, for you know, aircrafts in space, how
Yeah.
do they generate thrust, and what type of engines do they use? Fuels do they use, and how do they operate in a vacuum space, and does aerodynamics affect for those type of aircraft that's like outer space?
Okay, I really like how you couched 10 questions in that one question. But
Thank you, sir.
well done. I think this is honestly what we're going to discuss next week. I'm not bumping you off. I will give you a short answer now. What you're referring to is something called air breathing engines versus non-air breathing engines. Air breathing engines, okay, combustion to happen needs three things. You need oxygen, you need fuel, you need temperature, right? You need the trifecta of these three things to create combustion. Any two will not suffice. You need all three things. So when we think about air breathing engines, which is, let's say, our regular engines on our regular airplanes, you take in the oxygen from the atmosphere, you suck it in, and that's why it's called air breathing. As you rightly pointed out, when you go into space, well, there is no air, at least not in the conventional way we think about it. So you can't really rely on something being sucked in from outside the engine. So you have to carry it yourself. That's why you carry the oxygen, you carry the fuel, and you find a way to ignite it. That's what rockets do, right? So you have solid rockets, liquid rockets, where you carry your oxygen and you carry your fuel. We do talk about what different aspects of these engines are next class. So perhaps can I request you to hold off on to that? The
Yeah, yeah.
second part of your question is still valid. I can answer that now. You asked if aerodynamics make any sense. Well, when you're in space, no. You can have fins, you can have wings, you can have these aerodynamic objects which are really useless because there is no airflow around them to create any forces. But these are still objects that have to take off from Earth if you're taking it off from Earth. So you still have to go through our atmosphere where there is air. So yes, those aerodynamic devices would still be useful within our atmosphere to get to outer space, after which it becomes redundant. Is that okay?
Yeah, okay. Thank you, sir. I'll hold on and probably I'll find my answer from the next
Yeah,
week's.
if not, just fire the
Yeah.
same question next week and we'll discuss.
Okay, sir. Thank you.
Yeah.
Thank you.
Sounds good.
Means a
Okay.
lot.
Yeah. Pranay, do you have a question?
Yeah,
Yes,
sir. So, sir, my question was that why do aircrafts like the F-15 and the F-35 have two fins at the back, while as you would see in conventional airplanes, you would see only one, right?
I'm trying to remember what fin you're referring to. Hold on.
The dorsal fin, the one at the back.
You mean the horizontal tail?
No, no, no. The
Uh,
upwards one, the vertical one.
okay, okay. You're asking, got it. So those are the vertical tails. What are you asking?
Why does the F-35 and the F-15 have two of them,
Yeah,
while the other in a general aircraft you would see only one?
correct. This is a great question. This is actually a question on design. And maybe if I go back to Adi, can you just scroll up on your journal to the previous image? Yeah. Okay, that's fine. That works. Either one works. So here you have a single vertical tail, whereas in some fighter aircrafts you have two. Now, few things. The whole point of the vertical tail is to provide what we call as yaw stability and yaw control. Okay, such that if an aircraft is going straight and there's a small disturbance that comes sideways, you don't want the aircraft to move in an arbitrary direction. You want it to still be pointing forward. Okay, there you go. Right. So here you have two fins and here you have one. Yeah. So first function of the vertical tail is to give you yaw stability. Secondly, you want to be able to control the yaw. So there is yaw authority in that sense. So, and because these are effectively airfoil surfaces, what is going to dictate the amount of force that you get is effectively going to be the area. So during design calculations, you would have decided I need so much wing area for me to be effective. If I were perhaps what happens is, especially these fighter aircraft, if you have one single surface, it tends to be really, really tall. And that can affect a lot of the other aspects of the aircraft. Anything from how it handles to the structural weight being too high to a very simple fact, some of these aircraft are supposed to be stored on ships. You have a height constraint. So you may not be able to put a member that is really, really tall. So you say, well, I can't have one tail. I will break it into two tails. That could be one reason. The other thing you have to appreciate is a fighter aircraft. Okay, you always have a trade-off between stability and maneuverability, right? If something is very, very stable, it's not going to be maneuverable, which means it's not going to be responsive to many inputs, which this is a characteristic you like for a passenger aircraft. You want it to be stable, you want people to have a comfortable journey in there. You don't want people sitting in the aircraft and getting thrown around, etc., etc. I mean, it's just not a pleasant feeling. Nobody's going to come and buy your aircraft or sit in your aircraft again, and that's just a hopeless business model. On the flip side, when you're a fighter aircraft, you don't really care about it being very stable. You want it to be responsive. You want to say, hey, if I give you an input, I want the airplane to turn as quickly as possible and as efficiently as possible, right? Because that's what you want a system that is agile and that can move quickly. So when you do that, you tend to trade off on it not being very stable. So some of the considerations that go into designing the vertical tails, particularly for a fighter aircraft, is to try to give it sufficient surfaces such that it is very, very agile and quick. Those are some of the reasons why you see different design choices being made. What actually happens, people do both, and then they go through the pros and cons, and then they decide, well, this is what makes sense. So in that sense, design is not a very arbitrary procedure. The question that you asked is perfectly valid, and the only acceptable answer to that should be, okay, let's do it for a single one, let's do it for two, and let's study the pros and cons, and then let's pick what's good and what's not. You're never going to get this is a completely better solution compared to the other. It's always about what are you willing to trade off, right? All of aerospace is a trade-off. You just have to pick and choose your battles. Does that help? Yes, of course. You don't have
Perfect,
to.
sir.
Yeah.
Thank you so much.
Adi, you don't have to be so polite, Anuj. You can just go ahead.
No, no, sure. So, I mean, adding on to the same point, given that these are fighter aircrafts, okay, it's also important for you to escape from any other missiles. So you can't be having large surface areas just protruding out from your aircraft. So you need to make sure that you don't give away too much area for some missile to come and attack from a particular direction or something. So you need to also minimize how much you show. I mean, from an aircraft
Yeah,
perspective.
that's a great point. Actually, another way to put exactly what he said is you want to minimize your radar cross section. And you also don't want to be detectable. So if maybe one, yeah, and that's a strong factor. Yeah, thanks. That's a great answer. Yeah, Pranay, I hope that was okay.
That's perfect, sir. Thank you so much.
Okay. We'll tag team, yeah. I'm going through, I know a lot of you have raised hands. I'm giving chances to those who have not yet asked the question. So please don't be too upset with me if I don't pull you up immediately. Dhruv,
Yes, sir. So I was looking into some special types of aircrafts, and apart from the typical ones that I've seen, I've also seen some disc-shaped aircrafts, and I was wondering what is the aerodynamics behind that?
can you give me an example? Is it similar to the UFO that we just discussed?
It's similar, but it also contains like a brisk essence of these tip.
What? Sorry. Hello, Dhruv, can you hear me? Hmm. Yeah, I'm not fully able to understand what disk we're talking about. Um, I guess when your audio is back, can you just clarify that?
Yeah, yeah, hello. Yeah,
Yeah,
so
go ahead.
yeah, what were you saying? Could you repeat that?
I'm just saying I couldn't picture an aircraft like this. So do you have an example or something that maybe we can just search on the internet and throw a picture up?
Uh, Let me just check. Just give me a second.
Sure. Would you mind if I
And
cycle?
also, another question. Apart
Yes.
from that, I've seen certain Mark 5 aircrafts. Instead of having a tip-shaped, like a sharp-tipped wing, they have a blunt wing. What is the reason for that?
You've seen a hypersonic vehicle with a blunt tip?
Uh, like more towards Mark 5. They're like it's a bit unusual for me to see that, and I don't know why.
Yeah. So, okay. I'm not. Did we discuss Mach number or is it?
Yes, sir. Within the, I think so. Was it
Okay.
four? I think so. Maybe it was. Yeah.
Maybe it's
Four
next week,
plus.
but it's fine. Like I said, I'm not bumping you off. I'll give you a short answer, then we can take the longer answer. Mach number is effectively a ratio of, say, your speed to the local speed of sound. So if
Yes.
you're flying at Mach 1, you're flying as fast as the speed of sound. If you're flying greater than Mach 1, we call it supersonic flight. There is a subcategory of supersonic flight where loosely it is 5 and above, which we call hypersonic flight. And actually, there aren't too many uh, airplanes out there at hypersonic speeds. In fact, DRDO did a test a couple of months ago, which showed 1,000-second flight of a hypersonic test bed. So I'm not entirely sure what wings you're talking about. Maybe this you can clarify next week when we discuss. Because the typical airfoil that we see is actually good only for subsonic flight. They're actually very poor when you start going to supersonic flight. And in fact,
Oh,
the airfoil shape that you would see around a fighter plane is slightly different compared to a subsonic airplane. They actually are more sharp, and that's because of the flow characteristics that happen when you go past Mach 1. Hypersonics, as such, I don't even know if you would use traditional wings. There are some things called wave riders, which are just again geometric shapes, which will help you get the lift in a particular direction. So, long story short, I'm not entirely certain of any blunt shape leading edge surfaces on hypersonic vehicles. However, I look into it to see if anything is there, and we can pick this question up next week. Would that be okay?
okay, sir. And
Yeah.
also, sir, one of the examples of the disc-shaped aircraft is, I think, Watt V173.
Can you spell the
It's a
first one?
old type one. It's sort of like a flying pancake, you could say.
Could you spell
It's a
the first one?
Watt V173, VOUGHT.
Excuse me, sir.
Uh, 1 minute. Dhruv, Adi, could you just see if that's something there and you can throw a picture of that on your Zunar page?
I may not be able to share right now. I'm
No,
currently
not.
like,
I think Adi Narayan would. So I'm asking him.
oh, okay.
Yeah.
Yes.
Okay. He will, when he, wait, maybe you've already put it. Not yet. Oh, okay. Is that what you're referring to?
Yes, sir.
Okay. Yeah. So this is interesting. This is, it's still, okay. There is a classification of aircraft called flying wings, where effectively the whole vehicle is just one big wing, right? And here, that's exactly what it does. You minimize the fuselage. My guess is these are largely experimental in nature. You have the two huge propellers in front, which will propel the aircraft forward, and you have a flow that happens over the entire body of the aircraft, which is a wing, to generate a lot of lift. So the idea here is to try and get rid of the fuselage, which is not an aerodynamic body, and try to make the entire vehicle a flying wing. Yeah, in general, the same principles that work for overall wing would work here as well, except the entire airplane itself is just thought of as a wing.
Oh,
It's an
okay.
interesting design. That's really it. How
Okay, sir.
useful it
Thank you,
is?
sir.
Yeah, yeah. Cool. Let's see who
I guess
else.
the V2 Spirit is a better example than same. I think in terms of flying wings, we talk about it.
Which one?
The Northrop's aircraft, sir, the flying wing, V2
Yeah.
bomber.
Yep, sure. That's fine. You can throw that up also up there. You can throw the
Sure.
beam. I think Ritikesh.
Yeah. Can you hear me, sir? Can you hear me, sir?
Yes, I can.
Yeah, sir. I'm having a doubt in how much time a normal passenger aircraft and a blended wing aircraft can fly in air without without engines, sir.
Huh?
Not without
How?
engines. Shutdown. Engine shutdown on midway while air.
Okay. So this is a good question because it highlights one of the common misunderstandings of comparison. Right? When you make comparison between anything, point A and point B, it's hard to answer without knowing what is it that you're holding constant. Okay, it's like, for instance, it's a good question actually because it really highlights when you look at pros and cons of one versus the other. Sometimes we are programmed or we have a bias to say, oh, this is better or that is better. It's like saying, is the Concorde better or is the World War II plane better? And I assume we would pick one or the other, but it is really an incomplete question because I didn't ask you better in what, and I didn't ask you what am I trying to do with? Of course, you did say that, yeah, which one can fly longer. But the truth here is I can game your question to be whichever way I want it to be. I can have the blended wing lose an engine at say 10,000 meters, and I can make the conventional airplane lose the engine at 500 meters. So obviously in that scenario, the blended wing is the one that's going to fly furthest because it happens to be the higher. Even if you say they are both at the same altitude, I will say I will create one to be faster than the other, and therefore it may fly longer than the other, right? So the question is, or even if you say it flies at the same speed and it's at the same altitude, I'll make the blended wing obnoxiously large and I'll make the other vehicle wing really small, such that a small wing is, of course, not going to fly further compared to the blended wing. So, in all these questions, we can, unless the bounds and constraints and the problem is defined properly, you can always find a loophole to say, I can make anything win whichever way I want it to win. But I suppose the true one of the answers perhaps to the question is which one is more efficient? Maybe that is a question we want to ask. Is it a regular wing or is it a blended wing? And the answer is we don't. You have to ask for a certain weight class, for a certain airplane that has, let's say, if I say I have an airplane that weighs 10 tons, and this 10-ton aircraft is going to be at 10,000 meters and it's going to lose its engines at 100 meter per second. I'm just picking some numbers off my head. Then we can ask which airplane, if I had configuration one with a blended wing and configuration two with a regular wing, which one would fly further? I'm sure we can come up with an answer. But then the other question to ask is, why did you pick this scenario? Right? If it's just a pedantical question, that's fine. It's perfectly valid. You can always come up with an option and say, yeah, this is why it works. But what we really try and do in design is we say, I build an aircraft that has to do all of these things. It has to take off, land, fly at these altitudes. It has to roll. It has to maneuver. It has to have these safety features. It should operate without one engine at these altitudes and these airspeeds. So the whole laundry list of items that an airplane has to satisfy in order to be credible. So the ultimately, I will not be able to right now say A or B, but you need to do a detailed analysis and then show quantitatively, hey, this is why this is better. But I may not have answered your question directly, but I just may perhaps want to take this opportunity to highlight the importance of uh, comparing with parameters fixed.
Okay, sir.
Yeah. I'm not bumping you up. It's really a good question, but it is hard to answer it.
Okay, thank you, sir.
Yeah. Kanishka?
Yes, sir. Good evening.
Good evening.
It was once mentioned that during landing, lift should be equal to weight while it is descending.
Yeah.
How is it possible when the aircraft is still airborne?
So if lift is not equal to weight, then it will sink, correct? But
Yes,
it will
sir.
do so while it is accelerating. If lift is equal to weight and still descending, you can have a non-accelerating flight, but the velocity keeps decreasing. The equivalent to this is, let's say you're cycling, and you can be cycling such that you can maintain any speed that you want. That would be a constant velocity but zero acceleration. Or you could think of a scenario where you are pedaling faster or you're slower, such that you are increasing your velocity or decreasing your velocity, but that is an accelerating motion where there is a change of velocity with time. So when we talk about landing, we want to do it. It is possible to get into a scenario wherein, let's say, I will explain the sequence of events. Let's say you're now flying level, so lift is equal to weight, you're just flying straight. Then you switch off magically, let's say you reduce the lift, then your weight becomes greater than your lift and you start dropping down. But this is an accelerating flight because weight is greater than lift. So you're going to start dropping down faster and faster. At some point, I can then increase my lift again such that lift is equal to weight, but I am now maintaining a steady rate of descent. So it is possible to get into a flight condition wherein you are losing altitude, but you are not accelerating, which requires lift to be equal to weight. Does that make sense?
Okay, sir.
The
Yes, sir.
key, the key difference here is, are you descending in a zero acceleration scenario or a non-zero accelerating scenario. That will define if lift is equal to weight or not.
Okay, sir. Thank you.
Okay. Sarvesh?
Yeah, thank you, sir, for giving me this opportunity. So my main question is, there are aircrafts like the Sukhoi S-70 and the B-2 Spirit Bomber. They don't have vertical stabilizers, so how do they maintain yaw stability, even with fly-by-wire?
Yeah. Can we maybe throw a photograph of this just so that everyone is aware? The Sukhoi S-70 or which one did you say? The B-2?
B-2 Spirit Bomber.
Yeah. Adi, can you pull up any one of those two?
Oh, the B2 is there, sir.
Sorry, I'm on the wrong page. Okay, there we go. Yeah, this is a great image of the B2. All right. So your question is there is no vertical tail. So how do you stabilize it? And the short answer is you don't. Right? If you have even the B2 bomber, Adi, can you just draw some control surfaces on the left and right towards the ends of the wings? Just scratch some red box or something. Yeah, something like that is fine. Okay, so in this case, you will not have absolute yaw stability like you would with the presence of a vertical tail, but you can still try and get yaw stability by carefully deflecting these or by changing the thrust of the engines, right? So another option to get yaw stability is to think about if you have two engines, you can fire one and not fire one, and that will also create a force mismatch, which will create a couple. Now, in all of these, it's a great question because you would ask, why do you not have a vertical tail here? And the reason you don't want to have a vertical tail is because this vehicle was designed specifically for stealth, which means it has to have a minimal radar cross section. And having a vertical tail would increase its radar cross section. Yeah, there you go. Great picture here, right? So what do? The penalty for not having it is you are going to suffer a loss of yaw stability or yaw authority. So you have to compensate for it through other mechanisms. You may do that by carefully contouring the airflow on top of each side of the wing, or you may have a couple between. You see the control surface are placed at an angle that actually can give you a little bit of yaw authority also. But the problem is the minute you do a yaw, you get some yaw moment, you will also get a pitch or roll. So in a conventional aircraft, you can get roll separate from yaw, separate from pitch. But in these kind of aircraft, they get coupled. It's like if you touch something somewhere, something else is going to happen. But that's just the penalty you pay. You just need a better control system to handle it. But the advantage is you have minimized your radar cross section. All aircraft are designed for a certain purpose, and you will never get something for free. You just have to deal with whatever the rest of it is. So in this case, I would say the answer is with a very strong control system. Is that okay, Sarvesh?
Yes, sir. Thank you.
Okay. You don't sound entirely happy, but okay. Spandana? Hmm. Spandana, are you there? Or? Okay, maybe some audio issue will come back again. Tarun?
Good evening, sir.
Hey, good evening.
Sir, my doubt is if the
Yes, sir.
Spandana, I'll come back to you after Tarun if that's okay. Tarun, go ahead.
sir, if the aircraft faces stall, sir, if the air, what does the aircraft do, sir? Will it fall down or will it lose its ability to gain altitude?
Both, right? So, big fall down is losing ability to gain altitude. But stall, let's start with what is stall. When you have an airfoil, again, back to the wallet, if you increase the angle at which the airfoil is seeing the flow, you can get more and more lift, which is beneficial up to a point. Beyond a point, you are no longer going to get that lift force and it's going to drop precipitously, which is what we call stall. Now, the problem is an airplane can get into stall And we don't want it because that's a non-ideal scenario, right? You don't want to be flying in an airplane and all of a sudden your wings are unable to produce lift. Yeah, that's really not something you want to do. So if what we okay, first thing is you try to avoid stall. Aircraft are designed such that the operating condition is so far from stall that you're not really at stall. But if you do get into stall, immediately the intention is to reduce the angle of attack on the airfoil. You start pitching nose down. You try to get the air back on the wings in a clean fashion so that you can recover from it. So yes, stall can happen, not ideal, but there are protocols that are there to recover from stall. Although stall is not something you would want to see on an everyday airplane, all airplanes have to be certified for stall recovery before they are put into business. There is a strict set of requirements that every aircraft has to satisfy. One of that is stall recovery, right? You cannot recover an airplane from any arbitrary altitude and velocities, but there is an envelope that says, hey, beyond this altitude and beyond this speed, show me that you can recover your aircraft. That has to be a demonstrated thing. You have to, during certification, take your aircraft, put it in a stall situation, get into stall, and show that you can recover safely, right?
Okay, sir.
Okay. Spandana, can we, are you ready now?
The same doubt, sir.
Same answer. Okay. I think Vartika, yeah, go ahead.
So am I audible?
Yes, you are.
So I had two doubts. First one, like I wanted to ask for a quick clarification. Is the project where we have to create a robot the same as the optional project we were supposed to do earlier, or is it a completely different one?
No, I think it's the same, but I will clarify that for you. I believe it's the same.
Okay, sir. So my second question was a little out of syllabus, but like it's related to aerospace and all that. So it's like, how do spacecraft navigate in deep space without like any navigation system, GPS?
Great question. How do you define deep space, though?
So like deep into space, light
Yeah,
years ahead.
light years ahead. Okay, so far the furthest we've gone is one light day, and that would be the Voyager. Voyager 1 actually got to one light day, I think March
Yes,
of this
sir.
year. So that would be the furthest, not March, no, that may be March. I'm missing some dates. Yeah. Doesn't matter. It's a good question because we don't have GPS. Um, at this point, there are two things to think about. You're there because you want to explore. You're really not trying to hit a precise gap anywhere, right? So you just want to go in a particular direction and you see what you see. And what we can do at best is if you have smart systems on board that can reference yourself to, let's say, constellations and stars, you can sort of figure out how you want to orient yourself, just like how you would think about celestial navigation back in the olden days with ships, right? People look at the stars and they decide, okay, you know what, this is north, this is south, and that's how we navigate. Same idea. You didn't have GPS, you didn't have anything fancy. You would just look up at the heavens and be like, yeah, okay, you know what, that's the direction I want to go. You could do that. Or any command can be given from, just give me a second. Any command can be given from Earth, but you have to remember these are radio waves, or which are basically electromagnetic waves, and they will, if you're a light day away, that will take a day for the message to be received, right? So in that sense, you can't do any immediate course corrections. You just fire a signal and you hope that you can get it. The third problem, which is subtle, is that you hope that the systems on board are still alive, right? You have batteries, and when you want to make course corrections, you typically make it based on, let's say, if you have small thrusters or you have solar sails or something of that sort. Even if you receive an information, you need to still be able to make the change. So when we typically say a satellite is lost or it has come to the end of its life, what we really mean is it has run out of fuel for its thrusters, and even if you tell me to turn, I cannot turn, right? So in short, deep space, we're just trying to go in a certain directions. You could do it through celestial navigation. More often than not, you're just going to give command from Earth, which is going to take a long time to reach, and it is what it is at this point.
Yes, sir. So one more question I
Yeah.
had.
Yeah.
It was like, how do engineers test airplane safety without crashing real planes?
It's a great question. How do you test it? Because you crash it all the time. No, it's not. Um, so the gestation period for an airplane from its inception, which is conception of a drawing, all the way to when it rolls out and you're ready to sit on it or fly in it, is 10 years. It doesn't happen very quickly. You have car companies rolling out cars every year. There's already a 2026 model, even though we're not in 2026, but that's how the automotive industry works. Airplane industries are far more slower for precisely the reason that you said, because it's very, very sensitive to safety. If you sit in a car and whatever it crashes on the road, you don't really care. You just, yeah, find something happen, you just sort it out and do it the next day. But if something with an airplane happens, yeah, it becomes instant uh, news, and there's a lot of eyes on it. People are very sensitive to airplanes and it not working properly. So consequently, you have to spend an enormous amount of energy and time to make sure it is certified. So you would do this at multiple levels. You would do this by first testing subcomponents on the ground. Um, for instance, let's say I certify my engine to be operational for so many hours, let's say 1,000 hours. You would actually test it on the ground. You would run it for 1,000 hours under representative conditions and make sure that it works. And in reality, you would never run it for 1,000 hours at a stretch. You would say, I will run it for 100 hours and I'll bring it down for maintenance. So every airplane has a maintenance cycle, and sometimes the maintenance on ground is greater than how long it flies. For instance, you may be looking at 4 hours of maintenance for every 1 hour of flight. That's how that's how much the industry is careful about all its components. And so you would do a lot of tests to make sure the subcomponents work. You would do a lot of simulations. There's a rigorous safety board which every airplane has to go through, and they have a huge set of requirements, right? In some sense, these are as stringent as you would for medical equipment, because you can't afford mistakes. These things have to work on the first try all the time. You're not going to say, oh, well, let's see if it works this time or not. No, you wouldn't do that. You would not put something out there in the field in the medical industry unless you were sure that it's going to work. That similar sort of rigor is applied to the aerospace industry. And then, of course, now with technology getting better and better, we can afford to crash airplanes because you also have unmanned aerial vehicles, right? As long as you don't put a human in it and you are in a safe test space, sure, test it out. It's okay. Miniaturize it, put it in a wind tunnel, have smaller models, fly it, try it. But ultimately, you have to do it with people on board. And that's where you have test pilots coming, right? There is a whole segment of aviators who are test pilots whose only job is to push aircraft to its limits and to really test the aircraft. And these people are actually mavericks in their own sense, right? They're actually far higher certified than your regular aviators, because their job is to test something to failure, right? And they're expected to get into uncertified machinery or partially certified machinery so that you can fly. So I'll keep rambling on, but in the interest of everyone's time, there is a long set of requirements, and you have a combination of experiments, model testing, simulations, and full scale tests, subcomponent tests, and full scale tests before you are actually convinced that this aircraft can fly.
Okay,
Okay,
sir. Thank you, sir.
fine. I think I'm going to take the last three questions here, and I'll sort of wind up with that. But I do want to point out, if you have other questions, we are really happy to answer it. Please put it up, write a question. Nothing is really silly. Don't ever feel like, oh no, this was not a great question to ask. Um, because I don't know, one is there is no such thing, and two, you are assuming I know all the answers to everything you're asking. That also may not be true, right? So we'll do our best to answer, and if we don't know, we'll find an answer. So please ask your questions, because this one is really for you. It's not for us. Okay, the whole session we're conducting is for you to have fun and you to get your questions clarified. And like I said, either get into engineering or not to get into engineering, it doesn't matter, but just ask your questions. But right now, we'll take the last three. So I'll go with Chandrasekhar.
Yes, sir, I am audible.
Yeah, you are.
Sir, I have a silly question. I know that, but I am curious on that question, sir.
What is? Go ahead. What's your question?
Can you explain about aerodynamics in boomerang?
Aerodynamics. What?
Boomerang.
Aerodynamics of a boomerang. Is that the question?
Yes, sir.
That is not a silly question. People do PhDs on this and don't get the answer. I don't know why you think it's a silly question. Uh, it's actually a really nice
That
question.
rise from my mind question.
So I couldn't hear the last part. What did you say?
The question rises from my inner mind, sir.
Yeah, absolutely. So it's a very good question. Boomerang aerodynamics is actually not trivial. The idea behind a boomerang is you want to chuck something and you want it to come back to you. So you're thinking of an object which you can launch in a particular direction and ultimately will find the vector back to you. That is not simple actually. If it was, it has a sort of a V shape. So you can think of V-shaped things when it's moving forward, and that would be a simple airplane wing as such. But what makes it more interesting and complicated is the fact that you have rotation. The minute you have something that is spinning, like a helicopter wing, each section of this boomerang or wing is going to spin a little faster. The one at the tip is going to move into the air very quickly. The one that is at the center is not going to move at all. Right. So there is a change in velocity pattern across the entire wing, which changes the force pattern that this experiences, which is going to cause it to effectively tilt in one direction or the other. Added to that, you don't actually throw the boomerang horizontal, you actually throw it at a certain angle. The truth is, when you throw it at a certain angle, at a certain rotational rate, you are able to calculate that you are going to get a consistent force in a certain direction. The equivalent of this is, let's say you want to make a turn in an airplane. Let's say you just want to do a long circular turn and come back. You know that you have to have the airplane pointed in some direction. So you have to have a roll angle, and then you probably have to have a small pitch angle. We know that in under these conditions, the force is going to be acting in a certain manner, such that if I wait long enough, I can form a clear loop. When we do it with a boomerang, this is a combination of the rotational effect of the boomerang and the angle at which you throw it. Beyond this, it is really difficult to explain visually the aerodynamics of it. So this is really not a silly question. I would suggest you start reading up, or you can even think of this as a long-term project if you're interested. But people have done a lot of studies on it,
Yes,
so
sir.
perhaps there are some papers on this also.
Yes, sir. Sure, sir.
Okay. Yeah, I'll take two
Thank you,
questions.
sir.
Sure. Spandana? Maybe not there. Okay, I'll come back. Sarvesh, do you have a question? Maybe these were just hands that were raised and not taken down. That's also possible. Fine. Bhagyashree, do you have a question?
Yes, sir. Good evening, sir.
Hey, good evening.
So we have seen about the different forces which is acting on an aircraft. So how these forces are being constantly maintained in atmosphere during a flight?
Amazing question. By the control surfaces, right? Because when we do it ideally in, let's say, our analysis, we assume the wind is always coming in a certain direction, it's nice and nothing changes. But in reality, that's not the case. You have a lot of wind gusts, you could be flying into a storm. So the wind that you're seeing is also constantly changing with time and space. The aircraft could not be going straight, it could be slowly going up or going down. The air that's coming in might have small changes in density. So the truth is you're flying in an imperfect medium. So you're going to have small changes that you will have to make, uh, which you would do through the control surfaces. Equivalent example, when you're trying to cycle on a flat road, it's never flat. There are small bumps. It's slightly inclined, slightly. The road is tilted a little bit. You make small changes either by pedaling a little faster or slower, or changing the angle at which you are orienting your cycle. All of those are the small minor corrections that you make to your motion. We do the same thing with airplanes through these control surfaces. So through the journey, you would have small changes in elevator, small changes in aileron and rudder to sort of negate these effects. because you will have small forces acting in different directions. This is the job of a control system, and this falls under a classification of control systems called disturbance rejection. Right, so you try and create controlled systems that reject disturbances. So what you're suggesting is there is a whole field of control system theory and controls which are called disturbance rejection, wherein small changes that keep coming, what should you change as an input so that you can negate it? Does that help?
Yes, sir. Thank you, sir.
Okay. All right, I think that's sort of the end of all the questions in this session. So I really hope you took something away from it. It was fun for me. Hopefully, it was fun for you. Thank you, Adi, again for uh, you know helping us out and for actually handling the other sessions entirely. Yeah, so I'll again say if you have any questions, please write it. We will respond to you. If nothing else, then have a good evening, have a good weekend, and we'll see you next week. Okay. Thank you very much, everyone.
Thank you, sir.
Bye bye.
Thank you, sir.
Yes, sir.
Yeah, bye bye.
Thank you, sir.
Thank you, sir.